Okay, today we're going to problem 9, 23, 26 of chapter 2. Problem 9, an insulated spherical conducting shell of radius A is in a uniform electric field. If the sphere is cut into two hemispheres by a plane perpendicular to the field, find the force required to prevent the hemispheres from separating. Part A, if the shell is uncharged. First, we know that the surface charge density induced by a uniform field is, we have a relation below, we have a formula below from equation 2.15. And here we take our electric field along the z direction, and the electrostatic pressure equals to sigma squared divided by 2 epsilon 0 taught to normal factor. By symmetry, only z component left. Therefore, the force on the right-hand hemisphere is below, and we calculate the integration, and finally we'll get the answer here. Next, if the total charge on the shell is Q, and therefore our charge density has a newtons here. And next, and the same, we only have the z component left, and we calculate the integration here, and we spend the square here, and do the integration, and finally we will get the three terms, and we define the first one is F1, the second one is F2, and the third one is F3. And notice that the F2 points in the same direction for both hemispheres, while F1 and F3 point in opposite direction. So therefore, the force required to hold the spheres together is just F1 and F3. That means we only the first and third term left to prevent the hemisphere from separating. Okay, the problem 9 is okay. And next, going to 23. The hollow cube has conducting walls defined by 6 planes, and the walls on z equals to 0 and z equals to a are held at a constant potential v. The other 4 sides are at 0 potential. Part A, find the potential at any point inside the cube. And we first from the Laplace equation, and we will know these 3 relations here below. And we just use the boundary condition to match the 4 zero potential walls, and we will get the we have maximum coefficient to 0, and n pi divided by a, n pi divided by a, and we define our gamma component as the relation below. And next, our general solution will reduce into in this form. And next, we use the boundary condition on z equals to 0, and it has to be potential v. And this term will drop into 0 and left fnn here. And next, we use the orthogonal integration. Orthogonal integration, and these 2 terms, orthogonal integration will give us 4 divided by part a squared. And these two terms will vanish if for even integer and values 2a divided by n pi for odd integer. So finally, our coefficient for fmn in odd integer will be like this. And next, we have the same potential V on the other walls. So we have the relation here. And finally, we will find the coefficient E and N has a relation between F and N. And in the end, we have our potential formula at any point inside the cube here. And next, evaluate the potential at the center of the cube numerically. Accurate to 3 significant figures. How many turns in the series is it necessary to keep in order to attain this accuracy? Potential at the center of the cube is potential of x equals x, y, z equals to a divided by 2. And we use the 3 values into our formula, and we will get the answer here. And we define this is potential Mn. And we can make a table here for 1, 1, the value here 1, 3 equals to 3, 1, and the value here 3, 3, 1, 5, 5, 1, 5, 3, 3, 5, and 5, 5. And finally, these terms, we only need to accurate to 3 significant figures. So we only need to consider the 1, 2, 3, 4, 4. We only need to consider these terms. And finally, we'll get the answer here. They should be equals to 1/3 V. And next, find the surface charge density on the surface Z equals to 8. And you just do the partial here. Easily find the surface charge density here. Okay. So the problem 23 is done. Next, for 26, the 2-dimensional region are larger than A, and phi will be smaller than beta. Is bounded by conducting surface at these 3 boundaries and held at 0 potential, as indicated in the sketch here. At large rho, the potential is determined by some configuration of charges and or conductors at fixed potentials. Part A, write down a solution for the potential that satisfies the boundary conditions for finite rho. And we use the Laplace equation in polar coordinates here, and we will get the formula below. And use our boundary conditions on these 2 walls, we will get some coefficient here. And the potential is dropped into this formula. And again, we use the boundary condition on the cylinder here. And we will get the relation here. And next, our formula drop into this form. And next, for part A, here is okay. Part B, Keeping only the lowest non-vanishing terms, calculate the electric field component E0 and E5, and also the surface charge density on 3 walls. Apparently, the lowest non-vanishing term corresponds to n equals to 1. So our solution dropped into this form. And we do the gradient on our potential. We will get the electric field, and the form just like this. And on 3 walls, we just take for this one. That means we should calculate the electric surface charge density on the cylinder on cylinder surface. So we take the E0 terms and we make the rho equals to A, to the radius A, and we'll get the charge density here. And these two terms just on the wall, the two walls, and the value is like this. And this is for part B. Part C. Consider the angle equals to pi. A plane conductor with a half cylinder of radius A on it. Show that far from the half cylinder, the lowest order terms of part B give a uniform electric field normal to the plane. And we take beta equals to pi, and the field will induce like this. The field will drop like this, and we take rho much larger than A. We will finally get to the answer here. And this direction, we can sort it into y direction. Okay, so finally the answer is just like this. And next, we have to sketch the charge density on and in the neighborhood, in the neighborhood of the half cylinder. So this is our charge density. And next, for fixed electric field strength far from the plane, show that the total charge on the half cylinder actually charged per unit length in this direction is twice as large as would reside on a strip of width 2A in its absence. So we recall that the E field equals to this one, and we use the definition of sigma zero we have used below. We have used the last page. And charge density on the cylinder is like this, and we do the integration, and the total charge on the cylinder will like this. And the charge density on the strip will equals to this one, and we have 2A length. Okay, we have the width up to 2A, so just times 2A on it, and we will get the answer here. So we have that the total charge on cylinder will twice the total charge on the strip. Okay. And next, for show that the extra portion is drawn from regions on a plane nearby, so that the total charge on the strip of this large compared to A is the same whether the half cylinder is there or not. So we can do the integral here to find out the total charge. And we again do the integral to find the relation here and solve it here, and we take the limits. L is larger than A, and the total Q will independent of A. Okay, so therefore the total charge without cylinder, just the total charge for strip, we have calculated at the last page, and we'll find these two terms should be equal here. Okay, so whether the half cylinder is there or not on the limit, the far from field, it is independent here. Okay, so so here we have to do all problems here. See you next time.